Okay, so for the second half of this week's work, we're picking up with all the same ideas that we've been building on earlier in the week. So we're still going to be working in the same overall simulation, our masses and springs basics, and then we're going to go into the stretch part of that simulation. And so when we get in here again, I'm going to click the unstretched length and resting position boxes so that we get those lines in here. And I'm asking us to basically apply the same ideas that we've been building on to determine what these mystery masses are. So we've got this green, blue, and red object all just with question marks in the middle. We don't know what those masses are, but we can figure them out. And the first step of doing that I asked you all to go through is basically the same steps that you all went through last week for the zero notch spring. So you're going to have to figure out what the spring constant, that K value, of the zero notch spring is here. And the way that I ask you to do that is basically use the 100 gram mass. You're still going to be using the ideas that we were building on, so I still ask you to draw a free body diagram with a gravity force acting down, spring force going up, and since that object, that mass that's hanging, is stably at rest, we know those forces need to cancel each other out, or all of the forces acting on this need to be balanced. And you could go through the exact same kinds of calculations that you all have done throughout the beginning part of this week. So my recommendation is, if you feel unsure about how to do those, go back to that Monday video, because I don't want to take too much time to review that in this video. But again, if that's something that you need to review, I would say stop looking over this for a little bit and go back to that Monday work and just sort of quickly review how we went through determining the K values in this Hooke's law equation. And I'm going to move forward assuming that we've already done that, and I'm going to make up some numbers just to sort of demonstrate what you all will do with that work and with results once you've gotten them. So let's say that we figured out that the spring constant for that zero notch spring was 5 newtons per meter. And we've got Hooke's law still, negative kx. And so now we could plug in this 5 newtons per meter that we know for this spring constant into our k. And then for this x, again, we're going to need to, just like we did earlier in the week, measure that. So that's not something that we're calculating here. That's just an actual thing that we're using the ruler in this simulation to measure. And the one that I ask you to do this for first is our green object, or this like mystery green mass. And you can measure this displacement. Again, make sure that you measure that using this ruler from the blue line, the unstretched length line for the spring, down to the resting position line for where the spring sort of stably rests with this mass attached. And so let's just say that I measured that it was 80 centimeters. Right. So I'm making that number up. I think it's going to be a little lower for you all there, but it's 80 centimeters is just the number that I'm using as an example. Now, in that other video, I also go over how to convert this 80 centimeters into meters. I'm going to sort of skip that step here, and I'm just going to say that that is equal to 0.8 meters. So that's also just a pattern that you could sort of recognize, is that I knew to move the decimal for centimeters, for some measurement in centimeters, over to the left twice to get it into a measurement of length in meters. And so now what you can do is plug in the stuff that we know here, negative 5, so that 5 was our K value, times 0.8 as our X value for that displacement, and that should give us, I believe, 4 newtons. That's the spring force. And you might be asking yourself, why is that answer finally positive? And let's go over why that is. So technically, this 0.8 meters or this 80 centimeters could be considered negative because this displacement is down. If I use my ruler, I can see that this mass has pulled this spring downwards, so that displacement could be negative, and so in the equation I really could have a negative right there, and then you could show the cancellation of those two different negatives so that we get eventually a positive or upwards force, which is what we would expect, 4 newtons as our upwards force according to our free body diagram there. Now, once we know that Right? Once we know that that's our spring force, according to our free body diagram, and I'll just quickly draw that again, we've got our gravity force having to be equal to our spring force. And so since we know that this 4 Newton force is our spring force, we know that that must also be our gravity force. And so if we use our gravity equation, right, we know that the force of gravity is a mass times 9.8. I can take that 4 newtons that I found for my spring force, plug that in for our force of gravity, and then solve for our mass. Right, so I'm going to erase some stuff up top just to make room for this, for the solution procedure, but some of you probably see where this is going. We're an algebra step away from finishing this problem, and all I need to do, and I'll rewrite what we have up top, is divide both sides by whatever is next to the variable that we're trying to solve for. So since we're trying to solve for this m, I'm going to divide both sides of the equation by 9.8, and that will get us a mass, let's see, of 0.41 kilograms. And that would be my final answer for what this sort of mystery mass of that green object was. So again, if you need to, review that Monday video, because I think that'll be helpful for these calculations. But other than that, you're really applying all of the same ideas for this week's work.